Welcome back to my series all about limits, limit properties, and limit applications. In the last episode, we looked at what it meant for the limit as x approaches infinity of f of x to equal infinity. In today's episode, we're going to look at what it means for the limit as x approaches infinity of f of x to equal L, where L represents a constant in the real numbers. Now, before I draw a graph, let's again think about what do these numbers mean. So we see x approaching infinity. So again, we're thinking about very large positive values of x. We're thinking, what happens as x keeps on increasing? And we see that that limit is equal to a constant. So we can think about, okay, so x is approaching infinity, and f of x is either equal or getting closer and closer to a constant. So what's kind of a way that we can quantify this? We say f of x is getting close to L. We can say that the distance between them is very small. And how do we describe the distance between two numbers? Well, we say that right here, the absolute value of f of x minus L is small, where the absolute value of f of x minus L represents the distance between f of x and L. So again, just like last time's graphical example, because x is approaching infinity, let's think about a point A, where A represents an x coordinate on our graph. Now A corresponds to a y value, right? So we call this y value f of A. Now again, like last time, we can think about all the values of x that are greater than A. So any of these x coordinates. So x is greater than A. And we think about, well, when we plot x as any of these coordinates, what happens to our f of x? So what we see, our f of x is any of these points on here. And we see that f of x is getting closer to L. So again, if you want to think about that by quantifying the distances, we look at this distance, where this distance is f of A minus L. And then this distance here is the corresponding f of x minus L. So we see, in this specific case, f of x minus L is less than f of A minus L. And now let's think about what happens when we change the value of our A. So we think, well, what if A is a bigger value? Then the cutoff where x can be greater than A is now limited. But we see that still we choose these values of f of x, and the distance between f of x minus L is less than the distance between f of A and L. And we might choose other values of A that are less, and we might see it's not true. But again, we know that this exhibits the limit that we want. And like last episode, it doesn't matter that this can work for any x coordinate. We're just caring about coordinates of x that are very large. So we know that there has to be some sort of A that we can find. Now, like last video, I want to see if we can do the reverse process. Instead of starting with an x coordinate and trying to find something, right, less than the absolute value of f of A minus L, let's see, can we start from some distance and then see, well, can we find that A? So can we start from some f of a minus L. And I don't want to keep using f of a minus L because we're trying to find an a, but also that might take a long time to write. So let's say we have some distance, and let's call that distance the Greek letter epsilon. Now let's see, can we find an a such that when x is greater than a, we can see that the distance between f of x and L is less than this epsilon, right? Where this epsilon represents that distance. Well, sure. Let's say a is here. Then we have our x values that are in this green area. So we see if we choose an x value to be here, then the distance between f of x and L is less than that distance epsilon. Now again, we can think about this idea with an even smaller epsilon, right? So we've chosen a distance, epsilon, and we want to see, can we find an a such that whenever x is greater than a, for all x values when x is greater than a, will that distance between f of x and L be less than the epsilon that we chose? Now, even though this epsilon is pretty small, we can still choose an a. Let's say a is here. So our x values are in this range and, going beyond. And so we can choose an x here. And so the distance between f of x and L is pretty small. We don't even have any room to write anything in there. So we see that it doesn't matter how small we choose our epsilon. We see that this curve is getting closer and closer to this dotted line, to this asymptote. And so we can keep choosing smaller and smaller epsilons, and it doesn't matter how small of an epsilon we choose, because we can just keep going, right? Let's say we were to extend this graph and choose an a, and then we'll find x values, right? All the x values, in fact, that are greater than that a will make it so the distance between f of x and L is less than this epsilon that we chose. All right, so now I've written up here on our board the rigorous definition of this limit. The limit as x approaches infinity of f of x equals a constant L. So, what does this mean? This means that we can find an L, right? The L that satisfies this property, such that for all real numbers, epsilon, right, which are also positive, right? Epsilon is a distance, so it's always going to be positive. We can find a real number a such that whenever x is greater than a, the distance between f of x and L, the absolute value of f of x minus L, will always be less than epsilon. And we can see with quantifiers, there exists an L in the reals, a real number L, such that for all positive epsilon, right, epsilon is also a real number, there exists an a, such that for all x greater than a, whenever x is greater than a, the absolute value of f of x minus L is less than epsilon. And again, if you're looking at this and you're like, this is a bunch of words, we can think about, we start with the epsilon. And epsilon can be as big or as small as someone puts. So in this case, someone chooses a really small epsilon. We can always find an x-coordinate, a. So no matter how close they're saying that f of x and L need to be, we can still find a real number a, such that for all those x values greater than a, so there's that cutoff, we see that whenever x is greater than a, the distance between f of x and L is less than epsilon. And that is what it means for the limit as x approaches infinity of f of x to equal a constant.